Hi, my name is Huck, and I'll be talking about hardness of bounded distance decoding on lattices and LP norms, which is joint work with Chris Pikert. So lattices are the fundamental objects of study in this talk, and lattices are geometric objects which look like regular orderings of points in space. More formally, a lattice is the set of all integer linear combinations of some n linearly independent vectors, b1 up to bn, which form a basis of the lattice. So in this example, n is equal to 2, and we get the lattice generated by b1 and b2 by taking all integer linear combinations of these points. So for example, we have 2b1, 3b1, b1 plus b2, 2b1 plus b2, and so forth. So the bounded distance decoding problem, or BDD for short, is a computational problem on lattices. So as input, we get a lattice basis b together with some target vector t. So here we have the same basis b1 and b2 as in the previous slide, together with this red target point t. And the goal of the BDD problem, roughly speaking, is going to be to output an especially close lattice vector to t when we're guaranteed that such a vector exists. So to formalize this, I'll need a bit more notation. So we're going to measure distances in terms of LP norms. And a focus of this talk will be to look at the complexity of the BDD problem as we vary the LP norm that we're working in. So with this notation, we can define lambda1 of L, or the minimum distance of L, to be the length of the shortest non-zero vector in the lattice in the LP norm. And the distance between the target and L to be the minimum distance between the target and some lattice point. So armed with this notation, we can define BDD more formally. So we said before that the input to the BDD problem is a basis B and target vector t. But in fact, we have some guarantee about the input. So namely, we're guaranteed that the distance between the target and the lattice is at most alpha times the minimum distance of the lattice. So you can think of it as guaranteeing that there will be some lattice vector inside this red circle, or more generally LP ball, centered around t. Then the goal of the BDD problem is simply to output a lattice vector which is inside this red circle, or a lattice vector which satisfies the BDD promise. If we look at the full lattice spanned by b1 and b2, we see that indeed this vector x lies inside the red circle. And so the goal of the problem would be just to find that x and output it. So there are a few things to note here. First of all, the BDD promise is stronger for smaller alpha. So the problem is potentially easier for smaller alpha. And conversely, if we can show that the problem is hard for smaller alpha, then we will have shown something stronger. So that's what's relevant for this talk. So the point x satisfying the BDD promise will be unique for alpha strictly less than a half, but the problem is well defined for all values of alpha. Finally, it's worth noting that when we talk about computational problems on lattices, including BDD, we usually think of runtimes primarily as functions of n, which is the rank of the underlying lattice. So why study BDD? Key motivation comes from the learning with errors problem, LWE, which is a core problem in lattice-based cryptography. Specifically, LWE is itself a distributional problem on a family of BDD instances, meaning that an instance of LWE is a BDD instance on some family of lattices. Moreover, Regev showed that LWE is hard on average, assuming that BDD is hard in the worst case for small enough alpha. So if you could show that BDD is hard for small enough alpha, then you would have showed that a key problem in lattice-based cryptography is unconditionally hard, and therefore that a host of cryptographic instructions are provably secure. So what's known about BDD in different parameter regimes? So in terms of efficient algorithms, we only know how to solve BDD for alpha, which is around inverse exponential in n, where again, n is the rank of the lattice in the BDD instance. In terms of cryptographic applications, particular bullet point 2 above, we get that LWE is hard on average if BDD is hard in the worst case for some inverse polynomial alpha. Not much is known about the complexity of BDD, which is key motivation for this work. But both in the prior work by Lubachevsky, Liu, and Machancho, and in this work, the focus will be on showing worst case hardness results for alpha, which is constant. And here we'll worry more about alpha as a function of P. So of course, it's a very interesting question whether we can sort of close these gaps between the algorithmic regime, the cryptographic regime, and the complexity regime. And we hope that our work is sort of a step in this process. So what did we do? Our first result was to show improved NP hardness of BDD. Specifically, we showed that for all P and for all alpha greater than some constant alpha P star depending on P, BDD is NP hard. So these values alpha P star don't have closed form expressions, but they can be computed numerically to high accuracy. And we can also get a closed form upper bound on these values as shown here to the right. So in particular, we show hardness of BDD approaching the unique decoding radius, which corresponds to alpha equals a half for large P, as P tends to infinity. So the unique decoding radius is sort of a natural barrier for showing hardness using all known techniques. So this is sort of the best we could hope for using sort of what we know how to do today. Moreover, our work improves on the work of Liu, Lubachevsky, and Machancho for all sufficiently large P, namely all P larger than about 4.28. Our second main result is the first fine-grained hardness of BDD in any LP norm. So our first result along these lines is analogous to the previous result. So we show that there's no sub-exponential time algorithm for BDD for all alpha greater than alpha P star, assuming the exponential time hypothesis ETH. So this in particular holds for the important Euclidean case where P equals 2, about which nothing was previously known either. Second, we show even more fine-grained hardness. So namely, we show that for all non-even integer P and all fixed C greater than 1, BDD P alpha is 2 to the n over C hard for all alpha greater than some constant alpha PC star. So like alpha PC star doesn't have a closed form expression, but we can compute it to high accuracy as shown in this plot below. Another way of thinking about this result is as a gap factor time trade-off in terms of hardness for BDD. So just as an example in this plot here, so this green curve is showing what values of alpha we get, say, square root of 2 to the n hardness for. 2 to the n over 2 equals square root of 2 to the n hardness for. Third, we show analogous results to the previous two results for BDD with preprocessing. So BDD with preprocessing is similar to BDD, except you get the basis B ahead of time and you're allowed to preprocess it in any way that you wish before getting the target point T. So one of the things that makes lattice problems hard is you might get a bad basis as input. But in the BDD with preprocessing problem, you're allowed to preprocess the basis arbitrarily as you wish, or preprocess information about the lattice in any other way before getting the target point T. So this could be a much simpler problem, a much easier computational task. We in fact show hardness results for this problem as well, analogous to the ones that we show for BDD without preprocessing. So next I'm going to go through the proof of our prior results, which all more or less follow the same framework. So namely, we give a reduction from a known hard problem, which is a variant of the closest vector problem, to BDD. So our proof takes the form of this reduction along with its corresponding proof of correctness. So in key to our proof is the use of this intermediate problem, STBDD. So informally, STBDD is a variant of BDD where a yes instance has S short vectors, has at most S short vectors and at least T close vectors. So this is sort of in contrast with in quotes, normal BDD, which corresponds to 0, 1 BDD, where we sort of are guaranteed that there are no short vectors and at least one close vector. Make this precise in the next slide. So our proof is going to have two steps. First, we're going to reduce from a variant of the closest vector problem to this intermediate problem. And to do that, we're going to use a gadget called a locally dense lattice, which is a lattice together with a target point T, such that sort of matching the promise for the BDD, ST-BDD problem, this gadget lattice and target are going to have few short vectors, but there will be many close vectors in L to T. And so we're going to instantiate our reduction with the gadget from the work of Agrawal, Stevens, Davidowitz, which works well for large P. So we won't use exactly the same gadget that they do, or we use a very similar gadget, but we use somewhat different analysis to study it. We adapt their techniques. The second step of our reduction is to reduce from ST-BDD to normal BDD, for some, where T is greater than, say, 10S, or maybe set equal to 10S. Our strategy for this is going to be to use lattice sparsification, which is a well-known technique where we sample a random sublattice that contains a roughly, say, 1/2S fraction of both the short and S short and T close vectors. So the high-level idea here is that if we do this sampling, then with some positive constant probability, we'll end up with no short vectors and still at least one close vector as desired. And then there's this sort of final step where we go from 0, 1 BDD to BDD as we defined it before, but that's just going to be a more or less trivial search to decision reduction. So I'm just going to describe the first two steps in our reduction. And in fact, I'm going to describe step 2 first. So I'm going to start by just assuming that we've shown that ST-BDD is hard for T greater than 10S, and then we'll show how to reduce that to 0, 1 BDD. So first, let me define ST-BDD more formally. So first, I need one more piece of notation to do that. So if the NP-ART is just the number of points in A, in a discrete set A, lying inside an LP ball of radius R centered at T. So then the ST-BDD problem is a problem where as input, we again get a basis B and a target T along with some distance threshold R. So here's an instance of the 2,4 BDD problem, a yes instance of the problem. So we'll parse this in a minute. So we said in the yes case, we're guaranteed to have at most S short non-zero vectors. So in here by short, we mean vectors of norm at most R over alpha. On the flip side, we're guaranteed to have at least T close vectors, but not just T arbitrary close lattice vectors, but T close vectors, which are binary combinations of the basis vectors. So that makes this a little bit different. And here by close, we mean that the vectors are within distance at most R of T. So let's look at this example so far. So this is a 2,4 BDD instance. So if we look sort of at the big circle around the origin, so we have that this has the radius R over alpha, and the circle around T has radius R, and that there are S equal 2 non-zero lattice points inside of this ball. In this case, just B1 and minus B1. On the flip side, if we look at the ball centered at T, there are actually 4 binary combinations of basis vectors. So that's 0, B1, B2, and B1 plus B2, which lie inside this ball centered around T. So this is a 2,4 BDD yes instance. So a no instance of ST-BDD is just simply one in which the distance between the target and the lattice is strictly greater than R. So I'm going to just say again that 0,1 BDD more or less corresponds to normal BDD. So BDD, as I originally defined it, is a search problem, but that corresponds to just getting a 0,1 BDD instance as input, and with the goal of trying to find the one or more of the close lattice vectors to the target. So let's assume let's look at the second part of our reduction. Let's assume that we've already shown that S10S BDD is hard, and show how we can reduce it efficiently to 0,1 BDD. So again, the technique we're going to use for this is random lattice sparsification, which was introduced by Cote in the context of lattice hardness proofs. So the rough idea here is we just want to keep sort of a random 1/q fraction of the points in our input lattice L. So more formally, we're given a lattice L as input, which is of rank n. We have some prime q. And if we sample a uniformly random vector A from zq to the n, and we define LQ of A just to be the set of all vectors, lattice vectors in L, whose coefficient vectors x satisfy this linear equation, that the inner product of x and A is congruent to 0 mod q. So it's obvious that LQ of A is a subset of the original lattice, since the original lattice is just the same thing, but just without this linear constraint. And it's not hard to check that, in fact, this set forms a lattice as well, a sublattice of L. So let's just look at what happens when we apply this technique to our example from the previous slide. So say we fix Q equals 2 and A equals 1, 1. So this just means that we keep all lattice vectors whose coefficient vectors x have coordinates which sum to 0 mod 2. So for example, here we've kept 0, we've kept b1 plus b2, we've kept 2b2 and so forth, but we haven't kept b1 or b2 or minus b1 or anything else like that. So here if we look, there are actually 0 non-zero points lying inside this origin-centered ball. So we've managed to wipe out both of those, but there are actually still 2 points inside of the ball centered at T. We've kept both 0 and B1 plus B2. So we've successfully reduced to 0, 1 BDD. So now let's step back a notch and look at how we reduce from the CVP problem, this variant of CVP, gap CVP prime, to ST-BDD with, say, T greater than or equal to 10S. So first I need to define this variant of the closest vector problem. So this looks syntactically similar to many of the things we've seen before. So as input as before, we get a basis and a target. And the yes instance is one in which there's a close binary combination of basis vectors to the target. And here we'll normalize everything. So we don't have a distance threshold R, we'll just normalize it so R is equal to 1. In the no case, the target is far, meaning a distance strictly greater than 1 from all lattice vectors. So notice that this problem is quite similar to BDD, just there's no promise about any sort of relationship between the distance between T and the lattice and the minimum distance of the lattice. So quite a bit is known about the computational complexity of gap CVP prime, and in particular its NP hard, which will allow us to reduce from it and show hardness of BDD. So what's our reduction here going to do? So we're going to reduce from an instance of CVP prime of rank n prime, meaning the underlying lattice is of rank n prime, to an STBDD instance of rank Cn prime for some scale factor C, it can actually be greater than or equal to 1. So what are S and T going to be? So if that S is going to be equal to this funny looking expression, and that T will be equal to 2 to the n minus n prime. So here, this expression for S just says that, so this is just the number of integer points or non-zero integer points in an origin-centered ball of radius r over alpha. It says that we're going to be able to upper bound the number of lattice points in our output lattice in a ball, in an origin-centered ball of radius r over alpha by the number of integer points in such a ball. Like meaning integer points, meaning points in Zn. So what does the reduction do? It works as follows. So remember, so B prime and T prime come from our input gap CVP prime instance, and this is the output. So we need to output a B, a T, and an R, which meets these reduction guarantees. So let's observe a couple of things about this. So first, why is condition 1 satisfied? So condition 1 is satisfied. Roughly speaking, this is easy to see because there's a bijection between integer vectors z and zn and lattice vectors bz. And moreover, for all such z, it's easy to see that the norm of bz has to be at least the norm of z. So you get this follows just by sort of projecting onto the last n coordinates of bz. Okay, so that's why item 1 holds. So, and notice that this doesn't require B prime T prime to be a yes instance of gap CVP prime, and just generally holds. So why is the second item true? So let's just sort of in general look at what the distance is between the lattice and generated by B and T. So we have just in order to analyze this, we can look at the distance between the all halves vector and the integer lattice. And it's not hard to check that this is equal to exactly n to the 1 over p divided by 2. Okay, so what this means is that if we have a yes instance of gap CVP prime, meaning that there exists an x which is within distance 1 of this form, that's a binary x, which is such that b prime x is within distance 1 of t, then we actually get a whole bunch of close lattice vectors to t. Namely, we get 2 to the n minus n prime of them by looking at all y's that are binary and of length n minus n prime. So we take our good x and concatenate it with one of these good y's, and then we get that bxy is at distance at most r of t. So this is straightforward to check using this observation above about the distance between the all halves vector and the integers. Okay, so both of these items were showing that we have a yes instance of gap CVP prime, then we in fact reduce to a yes instance of STBDD, where S and T are set as shown. So in the case for no to no, just again, this follows straightforwardly from this observation about the distance between the all halves vector and the integers, again, combined with sort of the guarantee that in the no case, the distance between the lattice, generated by B prime, and T prime is strictly greater than 1. Okay, so this shows that we've reduced from gap CVP prime to STBDD. But our expression for S is kind of funny here. So it's not clear exactly how to get some sort of expression that we can work with. This is just like a point counting function. And in particular, what we want to do, the game is going to be to pick the smallest possible alpha such that the ratio of T to S is at least 10. So let's see how we can figure out what alphas we can pick. So just, yeah, again, recapping from the previous slide, we want to pick the smallest alpha possible such that T divided by S, for these expressions that I've written here, or at least that ratio is at least 10. Where again, R and N are defined in this way as stated. And to do that, what we're going to do is we're going to use an upper bound on the number of integer points in a ball due to Mason and Liskow. So you don't need to worry about this function too much, but basically sort of gives a relationship between this theta function, which you can think of as a generalization of Gaussian mass, and the number of points in an LP ball around the origin. So this is going to be some function that we can actually optimize over explicitly. So we can numerically compute the right-hand side of this inequality to high accuracy, which will correspond to the plots that we saw before. Okay, so anyway, to achieve our goal, it suffices to show that this ratio on the right-hand side here is greater than or equal to 10. So all I've done here is I've used the definition of N, and then I've used this upper bound due to Mason and Liskow. So we actually get that if we divide the expression 2 to the 1 minus 1 over C times N divided by this expression, then that's going to be a lower bound on T divided by S. And hence, if we can show that this is at least 10, then we will have shown that T divided by S is at least 10. Okay, and then, in fact, just by taking nth roots of both sides and multiplying, it's not hard to see that really what we need to do is it suffices to pick an alpha such that this expression here is strictly less than 2 to the 1 minus 1 over C. So if we pick an alpha such that this inequality that I just wrote down holds, then for all sufficiently large n, the inequality on the left will hold as well. That's not hard to check. So accordingly, we define alpha PC star to be the smallest value of alpha such that this inequality I just wrote out holds, but potentially with as a non-strict inequality. But then if we pick any alpha strictly greater than alpha PC star, then we'll get what we want. We'll get that this inequality does hold in a strict sense, and therefore that T over S will be at least 10 for all sufficiently large n. On the other hand, if we aren't as worried about the blow up in the rank, then we can define alpha P star to be the smallest value of alpha such that the left-hand side of this expression here, all of this stuff, is at most 2. So then if we pick any alpha strictly greater than alpha PC, greater than alpha P star, then we can pick some value of C such that for all sufficiently large n, this inequality will hold. Okay, and so these alpha PC stars are what we're going to use when we're sort of worried about SETH type fine-grained complexity results, we're really worried about just how much we blow up the rank of the lattice, the underlying lattice, and then we're going to use these alpha p star numbers when we're worried about NP or ETH hardness. Okay, so that concludes a description of our reduction. So open questions related to this problem. So of course, the most natural open problem is to show even better hardness of BDD in the LP norm. So a very interesting question is whether we can show hardness in the unique regime, meaning where alpha is strictly less than a half for some value of p. So this is actually not known for any value of p between 1 and infinity. We actually know hardness at exactly alpha equals a half for p equals infinity, and we know it for alpha equal half plus epsilon for p equals 1. But we don't know any sort of worst case hardness like NP hardness for alpha strictly less than a half. Another interesting question is if we can somehow do gap amplification, meaning that if we know that BDD alpha is hard, can we somehow do some sort of operation where we then get that BDD alpha prime for a smaller alpha prime is hard as well? So some sort of gap amplification along these lines is used to show hardness, strong hardness results for the shortest vector problem by a technique called tensoring, but that doesn't seem to work for BDD, at least in kind of a simple way. So another very interesting question is whether it's possible to show deterministic hardness of BDD or of the SVP problem for any finite p. So currently this is unknown, and it's a major open question, especially for SVP, but these problems sort of seem to be joined at the hip. Really sort of the key ingredient in hardness proofs, sort of base hardness proofs for both BDD and SVP, is a construction of so-called locally dense lattices, which were the gadgets we use that had sort of a lot of close vectors and not very many short vectors. Or actually maybe here, if we're not going to sparsify, like to get a deterministic construction, we want a lattice with, say, many close vectors and no short vectors. So the final problem is to show improved hardness of the unique shortest vector problem, USVP. So this is a problem that's closely related to the BDD problem, but about which not much is known in terms of complexity. So to conclude, we studied the bounded distance decoding problem, BDD, which is an important computational problem on lattices, and especially important in the context of lattice-based cryptography. We gave new and improved NP and fine-grained hardness results for BDD and for its cousin BDD with preprocessing. All right, thank you very much for listening to this talk, and I'd be very happy if anyone emailed me with questions.